Okay, so we're at a point, pretty close to a point where we can do some honest to goodness measurements. Okay, so now you're going to notice the photo gate here. So your old buddy, the photo gate. So you've seen her before, right? And so she is sitting there, and she's attached to the iMac computer. Okay, which doesn't have anything on it right now. Okay, so and then the piece of cardboard flag, the pink flag attached to it. Okay, so we can easily know the size of that, right? We can measure that. And so when the whole system is turning, it can pass through the photo gate. Let me get over here, you might be able to see it a little better. Okay, so the flag passes through the photo gate, and therefore if we know that distance, the size of the flag, and the time interval that the computer gives us. So the distance divided by time would give us approximately the velocity at the time while the ring is turning through the photo gate. Okay, it's going to be a little bit approximate because, well, in the later measurement it's going to be accelerating, not a constant velocity. But we're finding an average velocity for a brief time. So we just hope that average velocity will be, reasonably close to what the instantaneous velocity would be over a short distance interval like that. Okay. Now, there's one other problem that we have to deal with, and that is friction. There's going to be friction in this system, in the rotator itself, maybe a little bit in the pulley as well. Okay. Now, the equations we're going to be using later to find the moment of inertia, the big thing we're going to find, they don't consider friction. They just assume a constant acceleration. All right. And we have got to find some way to take friction into account. Okay. So what we can do, and this is what the manual tells you to do, is you put some mass on the hanger here on the end of the string, and just by trial and error you find an amount of mass. Let's wind this up here, where you find an amount of mass where when this turns, it turns pretty much at a constant velocity. We gave it a push to start with. We gave it an initial velocity, but that's okay. That's not a problem. If it's turning at a fairly constant speed, then that means that the mass we're putting on the string at that point is creating a torque that just about cancels out the friction. So that leaves it to rotate at a constant velocity. Okay, fairly constant. It's going to be a little bit rough, but it's better than not trying to do it at all. Okay. Now, one thing I might mention is I said that this would be rotating at a constant velocity. That doesn't mean that we just have to eyeball it and make a rough judgment. We can do a little bit better than that. We can take a measurement with the photo gate on the computer, and it'll give you time intervals. Okay, I'm not doing it right now, but this is how you would do it. Okay, so if we get time intervals on the computer that are fairly consistent, fairly constant, then we could assume, okay, we're moving at a constant velocity then, right? We don't even have to calculate the velocity. If we just look at the times and see that they're fairly constant, then we're moving at a fairly constant velocity. Okay, and I will, when I email you everything, I'll email you the data that I used to get that and convince you that it's fairly constant. What I found was that the mass that has that effect happens to be, let's see, 30 grams. Okay, so 30 grams hanging on the end of the string will cause us to rotate at a fairly constant velocity. Okay, so remember that number. All right, going to end this one, and you can come, then there's another video you can watch.